All right, I think we'll go ahead and try to get started. I know may have some people logging in still and logging in for the next minute or two, but we'll get going. We've got a few introduction type slides before we turn over to our guest speaker today. So first off, we want to welcome everyone. And as you can kind of see from our title slide here, we're kind of a joint venture today. This is our kind of Wednesdays are our regular user group dates for the Reynolds company. But with the topic being what it was or is around 5G, and we thought it was an interesting topic for the ISA section as well. So we went ahead and decided to kind of do a joint session today. So of course ISA usually meets on Tuesdays, but so we moved to today, and of course, you know, with the everything going on in the state of the world today, we're all social distancing ourselves as much as possible. So I know everyone's probably remote or at home or probably much more quieter office than normal. So so we appreciate everybody's kind of understanding. Of course, you know, we're not going to be doing a live seminar. So with that, we got a couple real brief introduction slides for both ISA and our typical ones for the user group. And I'm not going to take too much time here, but and then we'll turn it over to our guest speaker, who I'll introduce in a few minutes. But we'll start with the ISA business first. Again, we just want to always thank our sponsors. Very important to us. And as you can see, we've got quite a nice representation across many companies in the area. One of our sponsors is HMS, who is our guest presenter today. So that's why, again, the tie-in between the ISA and the users group. HMS is also an Encompass partner for Rockwell Automation. So we have we have I had a question pop up there from Art. Sorry. So we have a kind of a, you know, again, kind of a blending the two roles here together. Yep. And if I didn't introduce myself, I'm sorry. My name is Wayne Welk. So typically, Dean Bickerton might be kicking off the ISA section, our president, section president. I'm going to speak today briefly again on behalf of Dean to introduce ISA as well as the user group stuff. So yep, thanks. We start to kind of just start the steamrolling ahead there. Other business going forward in ISA is the digital archive. So we wanted to just remind everybody that, you know, again, with these times where we're all going to be kind of holed up and doing a lot of online work, we have a great archive of previous meetings, section meetings. You can always go back and watch those recordings. And we'll record today. We'll post today's presentation there as well. Same holds for our user groups. We have a rather extensive archive of our user group topics out there as well on our TRC automation blog. Last piece of business for ISA, just to know that keep an eye out on announcements, president's messages from Dean, social posts. Again, we got Facebook, Twitter, LinkedIn, and of course the website, neworleansisa.org for just for any news of any future events, right? So we know the world the way it is going forward. We'll probably be doing web seminars for at least another month or so. So just kind of watch for those announcements. And we might actually kind of combine, again, kind of do some joint seminars like we're doing today that might cover, you know, new technology and industry trends, as we have a couple of topics for our user group coming up that could be of interest to the ISA as well. So moving into the user group typical slides, just a reminder that we have a lot of different, you know, kind of seminars that we do throughout the year. User groups, kind of what we're doing today, just 1 hour technical seminars that are web simulcast, as well as the live audiences when we could get together. Dev days are usually half-day type events around the technology, kind of hands-on. IoT learning series, which was going to be something we were going to do in a couple weeks, but we're going to have to push that back to the fall with the HMS as well. And then of course, instructor-led training from Rockwell. But we do have a couple of user groups on tap, and this will be our kind of final slide here before we turn it over. And so next month, we got two topics coming up, I think, in April and May that I marked as ISA friendly, because we're not going to really be doing commercial type of presentation, but more technology type presentations. So in April, we'll do augmented reality topic, which will be of interest because there's a lot of buzz around augmented reality, AR, and of course VR too. Bringing that to the factory floor, so that'll be more of a discussion of just what are kind of the technology tools that are out there, and kind of what can AR really do for you on the factory floor. In May, we'll talk about industrial wireless networking. So just kind of the different technologies behind those wireless networking. We get a lot of questions a lot of times on just the various technologies and how do we bring things together wirelessly. So that's the idea of that topic. And of course, when we get into June, we will more towards a commercial, for the Reynolds company, but some ControlLogix redundancy design and application, as we'll have a new release of ControlLogix redundancy coming out around the summertime. All right, with that, Jason, I got your picture here off the web, but Jason Block is a solution manager with HMS Networks. He's up in Chicago, was going to be here today with us live and in the flesh, but we all know the story. Also joining Jason, who I didn't put his picture up, is Howard Greer. Howard is out of Austin, right, Howard, I believe? He's out of the Austin area and covers HMS Networks as a sales engineer. So he kind of covers this territory. So he's on the line as well. So with that, I want to let Jason take control of the screen and run the presentation from here.
Okay. Good afternoon, everyone. Thank you for joining us. So as I'm getting loaded up here, and let's see.
Yep, we got your screen there.
Excellent. Everybody can see everything?
Yep, I got you.
Excellent, perfect. All right, so dialing in here from lovely Chicago today, so thank you for joining us. Just a little bit of a warning before we get into this. I am working from my home. So on occasion, you may hear some encouragement from my four-legged cheering section in the background. So if you hear a little bit of background noise, my apologies in advance on this. So we'll go ahead and get started here shortly. So let's talk first about HMS and what our core value is. So this is the 3 slides that I'm going to do. That's just going to give you an overview on who HMS is as a company. So our core as a company is focusing on connectivity to networks, and then also developing IoT platforms on top of that for being able to take advantage of that connectivity and delivering results to certain applications and solving a number of things there. So as a company, we've been in business over 30 years. We were actually formed back in 1988. So we're celebrating about 32 years in business now. We're over 600 employees, and we have offices throughout the globe. From a customer standpoint, I mean, we've sold over 7 million devices so far, providing connectivity into different things. It's either machine level connectivity in industrial networks or connectivity to machines into various cloud-based platforms. So that's a lot of the things we do. And we're typically, our devices, you can be found in over 90% of the manufacturers that are out there, whether it's one of our brand labeled products that has our name on it that's sitting inside of a cabinet, or a piece of our technology that is designed into somebody else's product as well. And then we've basically done with our E1 service over 17 million VPN connections. And we play in a lot of different industries. We're in manufacturing, building automation, transportation, power and energy, water and wastewater. So if there's control or automation in some market, we typically exist there in some way, shape, or form. And we have actually the world's largest IoT network. So we've made our basically our history and a lot of our competency on providing remote connectivity for servicing. And as a result of that, we found kind of that early sweet spot in terms of applications that we can solve very easily for customers. So we actually have, as part of that, as scaling up and building that, we've developed the world's largest industrial IoT network. We have there for connecting machines and connecting devices and the systems there. And this gives you some of the metrics that we have behind that in terms of our registered users, our number of VPN connections, and so forth.
Just sorry, interrupt, but I don't. It seems like your slides may not be advancing for us. I'm not sure if possibly might be in some kind of presentation mode where maybe this, it's like trying to go to a second screen. Yeah, there you go.
How is it looking now?
That's it. Good.
Okay,
Thanks.
perfect. Yeah. All right. Excellent. Yeah, I think it was basically in presentation mode. Okay. All right. So you can see everything's good now. Okay, perfect. Thanks, Wayne. So moving on that, so we actually have 3 core brands that we use for providing connectivity. So this is kind of the hardware aspect of the equation. We do that with Anybus, we do that with E1, we do that with XI. Anybus is focused very much on device connectivity and machine level connectivity. E1 is very much on in terms of taking that device and machine level connectivity and then extending it up so we can actually have applications on that for remote servicing, for remote data acquisition, these type of things there. So those are kind of 2 of our core products we're talking about today. But we'll come back to the Anybus side of this. So Anybus is our brand that we have that handles a lot of our wireless technologies. So wireless has been a competency of ours and an interesting part of technology for us for a long period of time, which kind of feeds into the discussion topics that we're going to cover today in terms of 5G. So this is something that, you know, as this technology evolves, something we're paying very close attention to. And we'll actually be coming out with products here in the near term that are going to start addressing some of the things around 5G that I'll reference later on. But this is why this technology from an HMS perspective is interesting to us. As we've been in wireless, focusing on a lot of short range wireless networks. Now we're seeing basically 5G, which could be applied to both long range networks and also short range networks as well. So those are kind of our core brands and our competencies there. So with that, those are my 3 slides on what HMS is. Now I want to start getting into the technology themselves, from an existing wireless standpoint, what's in use today, and then I also want to start talking a little bit about the new wireless technologies like 5G. You know, what is going to be different about this? How is this going to address some of the challenges and limitations that we see today with some of the existing wireless technologies? So let's talk through some of those things and look at what are the current connectivity standards out there and some of the considerations that we have to keep in mind there. So if we look at it, wireless can really kind of be broken down in a couple of, areas of application use. So there's typically your long range technologies and your short range technologies. So short range technologies, we're typically talking things that are anywhere from tens to a few hundred meters is what we're looking at in terms of kind of the ranges that you're looking at there. And then long range technologies are typically those that can be applied over basically a long area. So instead of tens of meters, we're looking at tens of kilometers is what we're looking at there. So if we look at the long-range technologies that exist today, you can break those down in what we call public technologies, where it is something that is there's chipsets, things that are publicly available, the spectrum that is being used. So when I talk public, I'm really talking about the spectrum that is being used by these specific technologies that exist there. Is this something that requires leases, or is this something that is a freely available piece of technology there? So if we look at basically in the public technologies, we've got technologies like LoRa, we've got Sigfox, we've got 802.11ah, which is a newer technology, what they call the Halo, 802.11 Halo, that's designed around long-range wireless. And then we have basically areas that are kind of basically in what we call the private or the leased frequencies, and that are regulated by the FCC, and these areas there. Some of these are being made more available for applications, but they're still regulated to some degree. So there's some type of allocation or leasing body that manages these frequencies. And those include within the 4G LTE spectrum, this is the CBRS band. This is typically about 3.5 to 3.7 gigahertz on that spectrum. What is typically was formerly called the Citizens Broadband Radio Service. This is typically used for Navy radar in the past, but that is being freed up and allocated for more commercial applications there. So this can start to be used for what we call semi-private networks, where people can get certain slices of spectrum for their facility or their application. 802.11af was a precursor to 802.11ah, and if you have people who live in rural areas with wireless networks, typically they're using 802.11af, which runs over your traditional television frequencies, so things within the UHF or VHF bands that are there. So what are some of the benefits and challenges with each? So if we look at, the technologies, if we look at LoRa, I mean, one of the key things with these long range technologies is that they give you several, they give you significant ranges on this. LoRa is actually quite powerful, and that'll give you up to 15 kilometers of range, and it's actually low power consumption. And one thing about all these different long range technologies is they typically exist under 1 gigahertz in terms of frequency. So the lower the frequency, the more range you get out of that. In terms of those technologies. So typically your long-range technologies are all going to exist under the 1 gigahertz spectrum. Now there's some downsides to all of those in each of those cases, is that the data rates on those technologies are relatively low by comparison to some of the higher range, the higher frequency technologies. So LoRa is basically up to 15 kilometers of range. 4G LTE has longer ranges because the extensive networks that exist in place right now, and those can actually support higher speeds. So it falls a little bit outside the spectrum. So extensive network, and with cellular networks, they're much more tightly managed. So this creates a high degree of reliability with those networks because the access to the networks is managed. Sigfox is a lightweight protocol, very ultra narrowband for scalability. And one of the things that these narrowband protocols give you is the ability to penetrate into buildings. So you can actually send the signals can actually go through structures. And that's true. You can also see this with 802.11ah. So this is the extension of the range on the 802.11 standard, which is normally for about 400 meters on the top end, but you can actually go several kilometers with 802.11ah and also 802.11af. With AF, basically you have a lower power consumption. AH, you have reasonably high scalability with this. So reasonably high density of devices that you can add to this. Now, there are challenges with each. As I mentioned, low data rates tend to be a challenge with many of these protocols here. In the case of LoRa, there's not an extensive network, so it's not easily scaled. So it's very difficult to, even though you've got range, it's very difficult to have extensive numbers of devices connected to that network. 4G, the challenges there is it's a higher latency protocol, not necessarily optimized for control applications for wireless. And with Sigfox, with it being ultra narrowband, it can actually do some interference with wideband applications. So Sigfox doesn't always play well with other wireless technologies in the same area. And with 802.11, you're dealing with high latencies there, and also with 802.11af. Once again, that's a licensed spectrum. So based off of the area, that spectrum availability is inconsistent based off of, you may have television channels that are occupying pieces of spectrum there. So if you have devices that are moving from one area to another, there's reconfiguration that has to be done to adapt to that spectrum. Short range networks. So I think everybody here to some degree is probably familiar with 802.11. I'm connected to an 802.11 network right now. So you have the 802.11a through the AC standards that have evolved over time. So some of the advantages of that is relatively high throughput on these technologies based off of what you're using. And then, 802.11 is based nicely around roaming. So it's good for roaming applications and short area networks. So the ability to move between different access points and connect to the network at different spots is relatively seamless. You have the Zigbee technologies, which is starting to be used for a lot of sensor applications. It's extremely low power consumption and extremely scalable in the number of devices that you connect up. And it's extremely lightweight protocol, so very, very low data overhead with Zigbee on there. And then you've got your Bluetooth standards. So you've got your standard Bluetooth, and then we've got what is called Bluetooth Low Energy. One thing that Bluetooth adapts across the line is what is called adaptive frequency hopping. So if it detects interference or on a certain slice of its spectrum, it'll readapt its frequency hopping to avoid that part of it. And from a connectivity standpoint, Bluetooth actually has very stable jitter and latency. So the latency is not great, in terms of that. So it has a higher level latency, but it's an extremely stable degree of latency. It's predictable. So Bluetooth has that going for it. Low energy, of course, the key thing there is low power consumption. And it's also an extremely lightweight protocol. And it's infinitely scalable because it's typically with Bluetooth low energy, you don't have an always on connection. So you have that, you have that challenge. I'm sorry, it's not an always on protocol. So you have essentially your access points in your devices don't maintain a consistent connection. What it is that the Bluetooth Central wakes up the peripheral device, and that creates a connection there. So from that standpoint, it's infinitely scalable because you can build up as many devices as possible because there is not a fixed network capacity that you have there. There are challenges to each. With 802.11, it's very popular, so there's a lot of congestion there and noise associated with that. It's not easily scaled, so it's based off of Ethernet as a standard. So typically, if you're dealing with a subnetwork, you have about 255 devices that you can connect up to a standard network. And so it's not easily scaled from that standpoint. The latency actually can be quite variable with 802.11 based off of congestion. And then also you have to deal with surfaces. So with 802.11, with the higher frequencies, it's more susceptible to absorption and reflection that's involved with that. So the challenges with Zigbee, it's too unsecure for critical data. So it doesn't have a lot of security built into the stack and there to basically securitize the data. So it's good for small area networks where you don't have internet connectivity right at that point. But for basically kind of a broader, like a WAN type connectivity, it's considered typically too unsecure for critical data. Bluetooth, basically have the low data rate. And you have the scaling of the network is oftentimes very complex in those cases. So you can scale a standard Bluetooth network, but it requires having devices that can switch off between access point and network device modes to be scale out. But if you take just a standard access point in a device, you can connect up to 7 devices. So it's not very scalable. And with Bluetooth 4.0 low energy, typically your cheeky challenge there is you're dealing with very short ranges. So I want to get a little bit in. So one of the things I talked about with some of the short range networks was congestion, particularly 802.11. So 802.11 functions in both the 2.4 and the 5 gigahertz spectrums. So 2.4, being in those spectrums, one of the key things about it is that these are free, unlicensed parts of the spectrum that are out there, which means they're available for anybody that's out there. So there are a lot of technologies that use 2.4. You have 802.11, you have 802.15.4, you've got Bluetooth Low Energy, and you've got standard Bluetooth, all playing within that same spectrum. And if you look at 802.11, you've essentially what we have called is basically 3 available non-overlapping channels available to you, 1, 6, and 11. There are more channels in there, but they overlap with other channels in there. So if I have congestion at channel 1, it's not as simple as me moving over to channel 2 to avoid congestion. You have to either jump to 6 or 1, 6, or 11. So there's a limited amount of bandwidth there. And the more devices that you use on there, you've got this part of this channel here. The more devices you attach to that, the smaller those slices that are in there. So all those devices have to compete for that part of that frequency that's in there. in addition to potential interference or noise that you can get from other technologies that are producing, in that frequency space. And this is just from basically your standard network technologies as well. I'll talk a little bit about some of the other technologies that play in the 2.4 gigahertz space as well. Then you've got the 5 gigahertz spectrum as well, which you actually have a higher number of non-overlapping channels that are in here. Based off of, those can be combinations of basically 20 megahertz channels, 40 megahertz channels, up to potentially 160 megahertz channels. So you actually have a higher degree of bands that are available in there. But for most applications, there's really only a small number one that can be used with most radios, and that's what is called the Uni 1 and the Uni 3 spectrum. The reason being is that a lot of the radios out there, if they're going to play in the Uni 2 and the Uni 2 extended space, they have to have what is called dynamic frequency selection. And what this does is that if it detects, communications due to high priority communications, typically things like weather or military radar in those frequencies, it has to be able to readjust its frequency around that. So for most radios that may not have DFS supported on there, it has available to it Uni 1 and Uni 3 is typical there. And then if you're dealing with 40 megahertz or 80 megahertz channels, that reduces your spectrum significantly in terms of the channels. So with 2.4 gigahertz becoming congested, 5 gigahertz is starting to become the next refuge for people, and that's going to get congested over time. And looking from 2.4 to 5 gigahertz, 2.4 gigahertz typically gives you about 400 meters normally. 5 gigahertz, you're typically about 200 meters. So you're losing range when you shift to 5 gigahertz. So it makes it challenging for some, remote asset applications unless you're truly, local around that specific asset. So I mentioned application considerations. So with basically higher frequency technologies, things like Bluetooth, things like 802.11, materials tend to have an impact on these. So wood is somewhat negligible, typically about 3 dB of loss on there, and all the way up to concrete, which can be 15 dB of loss in 2.4 and 26 dB within 5 gigahertz. So if you think about most of the radios out there are typically, somewhere in the 13 to 20 decibels in terms of the power ratings of those. So when you start looking at things like solid metal and solid concrete, you're either dealing with basically 100% reflection or 100% absorption with most radio transmitters that are out there. So that's something that has to be a key consideration as well, is trying to get these things, wireless technologies to play in environments where you potentially have structures that you have to go through. These can be very challenging with a lot of the normal higher frequency spectrums that are in play today. Other thing is noise. So I talked earlier about the different wireless technologies that play at 2.4 gigahertz. So there are a lot of other things that are functioning in 2.4 gigahertz spectrum as well. So typically, if you think of portable phones, handsets, these type of things are typically transmitting at 2.4 gigahertz. Microwave ovens transmit at 2.4 gigahertz. And then you've got, typically your wireless microphones, and then you have all the different wireless technologies there that are transmitting at 2.4 gigahertz as well. So what you end up with in a lot of these situations is you end up with a significant amount of extraneous noise that's out there. And this can make it challenging for some applications. So if I have a signal of, 16 decibels, but if I've got 13 decibels of noise, I have a very, very low signal to noise ratio. So I've only got about a 3 decibel differential there that's on there. So this can actually lead to things like retries and critical applications that make it very difficult in certain things like safety and so forth. If I have a very high noise floor compared to a very low power level, and if I'm trying to do safety communications across this is going to create bit errors, retries, these type of things, and a lot of those applications there. So noise is one of the critical considerations there. And it's very challenging in 2.4 gigahertz, not as challenging in 5, but as more devices connect up there, the 802.11 spectrum is going to become congested in the 5 gigahertz space as well. So those are addressing some of the challenges with existing wireless technologies. One one of the things I want to connect on to move on to next is essentially some of the basics of 5G. So 5G, if you follow cellular communications as long, is the next generation in the cellular standard that's out there. So in 2001, the third generation partnership project came out with the 3G offering. So what 3G was when it came out in 2001 was essentially the first foray into unifying all of the different cellular standards around a single group of technologies that would be used by all the providers. So if you're familiar in the original days of cellular with basically the 2G standards that were out there, typically you had CDMA 2000, which was Verizon. You had GSM, GPRS, which is your AT&T. Around 2001, they focused on basically unifying this around one standard. And this was the offering of 3G that was out there. So the standard was 2001. You start to see networks start to be deployed through the back end of the first decade within the 2000s. So then we have basically 4G LTE, which migrated from there, which was the next generation after that. And 5G is the next generation after that. So it's viewed in many ways as a brand new technology, but it's more of an evolution of the existing technology that's out there. 4G was an evolution to address some technical issues that were found with the original 3G technology. 5G is now really is kind of taking the next step to apply itself towards a much broader degree of applications where we can actually think of 5G as a wireless infrastructure type protocol, infrastructure type standard. So I want to cover some of the basics of this. So there are three sections of the 5G mobile network standard, services standard, that are being pushed out there right now. And each of those provides certain benefits out there for different applications. So the three that is basically is called enhanced mobile broadband, ultra reliable low latency communications, and what is called massive machine type communication. And each of those sections of the 5G standard are geared towards focusing on specific benefits and applications. So the enhanced mobile broadband is very focused on high data rates. So this is when you've heard people talking about 5G technology as being able to download large movies in just a few seconds. This is where they're looking at enhanced mobile broadband. And this is something that is being derived not out of improvements with existing spectrum, but opening up new parts of the spectrum, typically in the higher frequencies, to enable these higher data rates. And be able to create more spectrum allocation so that we can actually handle a lot more traffic. So what we're finding is that within the current constraints of a lot of cellular communications, we're adding more and more devices every day, and we're pressing the limits of that technology there, those frequency spectrums. So now we've opened a lot of the higher frequency spectrums to allow for higher throughput applications and also more capacity. Then there's the ultra reliable low latency communications that's geared around basically extremely high network availability. And I'll talk through some of the ways in which communications prioritized. And then also from a radio to radio standpoint is getting basically the user end device back to the base station, getting those latencies down to be around 1 millisecond. They're not there yet, but that's the goal and what we want to get to there with that. And then what is called massive machine type communications, as more devices are being connected up to the internet. It's, how can we connect, instead of, a few devices or, 1,000 users using cell phones, how can I connect 1 million devices that are sensors or, that are monitoring different, pieces of equipment or applications there? And how do I do that with extremely low power consumption, low cost, basically low data overhead, these type of things there. So some of the use cases that we have on there are for ultra low, we'll start with enhanced mobile broadband, but those are going to be applications like autonomous vehicles, which have high data throughput, things like augmented reality, so advanced visualization solutions like that, remote access, so being able over cellular networks to connect up to a piece of equipment and create local network connectivity. and then also being able to monitor inbound and outbound logistics, basically things like fleet management is where we can see some things like enhanced mobile broadband, where we need to connect into basically moving networks is a way of kind of looking at that. Then we have massive machine type communication, which is typically, once again, that's about wireless sensor networks, being able to do some location tracking, GPS coordinates, some asset tracking, these type of things that are relatively low overhead and relatively low change, relatively slow changing type bits of data. And then we've got ultra reliable low latency communications. And this is where we see it long term, where this could have significant impacts on automation, where you can be able to do things like motion control over wireless networks, mobile robotics, being able to do remote control over wireless networks, and then mobile control panels with actually safety functionality built into them. So we actually look at over time being able to do safety functions over wireless networks based off of 5G. So what I talked about earlier is a little bit is I talked a little bit about increasing the spectrum availability. So a lot of cellular networks today typically have functioned down into the sub 1 gigahertz, into the 1 to 5 gigahertz parts of the spectrum there. That's where most of your 4G LTE and previous networks existed at that point. So with the lower parts of the wireless spectrum that's available to it. What 5G has opened up a significant amount of these higher frequency spectrums, and all the way up into this kind of the 64 to 71 gigahertz areas, what they call millimeter wave. So when they're talking about these extremely high data rates, this is really what they're talking about here. Is they're talking about this millimeter wave technology as a key component of 5G communications. Extremely high frequency, reduced range. As you go to the higher ends of the frequency range, you do lose some range out of that, so you require more infrastructure, more base stations that are in place there. But what you do get is much higher data throughput in those situations. And the millimeter wave is what they're starting to look at for some commercial applications, where there are some of the network providers are starting to drop fiber backhauls and connect it up to these more tightly condensed base stations that are going to be out there that will be able to provide millimeter wave technology. But this is the high end of the spectrum that's really going to provide the higher data rates. One of the things I want to kind of touch on here is this 3.55 to 3.7 gigahertz part of the spectrum. This is what I was referring to earlier, which is called the CBRS spectrum. And this can actually be used for semi-private networks. So you can connect to a service provider that is a spectrum allocation service provider that can basically take this band, which has now been made publicly available, and you can get your own slice of spectrum based off of your location. So you would basically give the spectrum allocation service a detail of your site, the size of your site, the power of your radios, and then they would give you a slice of spectrum that would be yours. And this is much less expensive and much more streamlined than going through a normal FCC process for acquiring licensed spectrum. So this is a very interesting technology for here, particularly in the United States, is this CBRS spectrum. Other countries are also looking at portions of spectrum that they can use for the same type of service there, but we're seeing that occur there. And then you've got also within here, you've got the 5 to 8 gigahertz, which is a publicly available portion of the spectrum as well. So that's public spectrum that's available there. A lot of the frequencies will be used by a lot of your cellular company providers. They're basically their public networks that they're offering and selling as a service. It's there. So some of the technologies that are built into this that I want to cover on. So one of the things that's kind of the core of 5G communications is what is called massive MIMO. MIMO stands for multi-input, multi-output. Really what it means is that devices have very dense antenna arrays in there and can incorporate things that are basically along the lines of beam forming. And this is something that's built in kind of the enhanced mobile broadband spectrum, in which in those cases with these highly dense antenna arrays can process signals from multiple locations. So the same user end device that's potentially, say, is using millimeter wave technology can transmit back to a base station, and that base station can take multiple signals from that endpoint and then either constructively interfere or destructively interfere to find the best pathway. So some of the things I talked about with previous wireless challenges is with structures, is that in this case, even though we're dealing with high frequency communications because of the massive antenna arrays that are existing in these devices, we can actually use structures to our benefit to find the optimal pathways for data to move through there. So in this case, the structures are actually serve almost to the benefit of communications in these cases. So if I have, mobile communications, then I can take advantage of these structures in those situations. Also, seamless transitions. This is another part of the enhanced mobile broadband spectrum. So if you're dealing with wireless, most wireless technologies today, if you're roaming from access point to access point, and for example, typical 802.11 structure, there's a handoff time that occurs when you're using wireless. With 5G communications and cellular communications, you can actually transition between base stations. You can actually connect up to another base station before you break to the connection to the other. So this is actually optimizes mobility even much more so. So if you have mobile assets that you're looking at there, mobile remote assets that you're monitoring, those cases you can actually connect up to different base stations seamlessly. So it establishes it can establish simultaneous connections as it's moving through there. So this is another core benefit that 5G brings into this. So also ultra reliable low latency communications. So we talked about this as one of the new standards that exists under there. So with standard messaging that occurs over, for example, like a 4G LTE network, with the standard protocols there, typically if there's a piece of data that has to be sent across, there's a series of authentication pieces that have to occur between the user end device and the base station before that data actually gets delivered. So you have different packets that get exchanged there, and that creates about, in the best case scenario, about 6 milliseconds of latency, in the best case scenario with standard messaging. With the ultra reliable low latency communications, they built in basically new protocols in there allow for what is called grant-free data configuration, where essentially the user end device is authenticated to create basically a grant to it. And then the data is actually passed, is passed across that through the stream there. So when the user end device creates a data stream to it, it's automatically delivered without authentication because everything is essentially pre-authenticated in that way. So that's one of the key things that ultra reliable low latency communication. So it reduces your 6 millisecond latency down to about 1 millisecond that we're looking on there. And this is going to, this is kind of the target that we're looking at as the radios evolve right now. We're looking kind of the near term, it's probably going to drop down to about 3 milliseconds. So it's going to be about a 50% improvement in the near term, but long term, it's going to be less than 1 millisecond. So this actually gives us the opportunity to be able to actually do control over wireless networks. So another thing that is built into ultra reliable low latency communications is what is called diversity. So one of the things that they're promising is 99.999% uptime. And that is basically built in is by creating diversity. So with frequency diversity, that is basically a way of replicating packets or communications or data across multiple frequencies within spectrum. So I may be transmitting at a specific frequency, but I might have multiple subcarriers under there that I am sending that data through. So I'm creating essentially multiple data pipes throughout there. And then you've got time diversity, which that comes into play there as basically as being able to send the same piece of data within multiple time periods. So repetition of the data. So that creates additional diversity there as well. And then there's what is called spatial diversity, which is essentially basically this multi-pathway approach to it. And this is what also comes away with basically the massive MIMO communication. So the the dense antenna arrays that exist within devices there. So that creates spatial diversity there. So what this does is this basically gives, creates a high degree of reliability for communications by merging these three things together, either through the modulation of the signal or through the structure of the communications and the redundancies that are in there. Also part of ultra reliable low latency communications is what is called enhanced mobile broadband preemption. And what this is that this is a way of creating essentially a higher level quality of service for certain types of data. So for our ultra reliable low latency communications data, it can actually preempt normal enhanced mobile broadband communications, and it can overlay its data over those communications. So it can break the enhanced mobile broadband piece of it and overlay high value information there. So this is another way of creating a high degree of reliability and also reducing the latencies, as well as by essentially what is used the concept of time sensitive networking to provide priority to certain types of communication. So if I am transmitting safety data over a 5G network, this is where the ultra reliable low latency communications comes into play, as it gives priority to those type of communications in terms of that. So this is where this particular chunk of data is built in. It breaks the parts of the MBB portion of the packet and is inserted in there with a higher degree of priority and quality of service. Then the last one I talk about is massive machine type communications. So one of the things I'm clear about is this. So in terms of massive machine type communications, this is kind of a basically a side evolution away from a lot of the normal communications that occur in terms of going to 5G. So a lot of the 5G that you're seeing, particularly in terms of the next generation radios that are coming out, are focused around ultra reliable low latency communications and also enhanced mobile broadband. So it's kind of this curve here as we go to category 19. But in terms of a lot of sensors and devices out there, they're typically very low overhead in terms of data packets. They're extremely low cost systems, and they oftentimes run off of batteries. So they can't, and they need to run off of batteries for a long period of time. So power consumption is critical. So typically they are using these different standards, the things like we call like narrowband IoT, things like Cat-M1. These are lower data rate, lighter packet communications that consume less power, that are actually perfect for sensor applications. So if I want to have a vibration or a temperature sensor on a pump motor, those things that oftentimes where the data might be so relatively slow moving or extremely lightweight, I can accept lower bandwidth applications. So rather than 10 gigabits per second, I may be looking at a few hundred kilobits per second is what I'm looking in terms of data rate. But because the overhead of the data packet size is so low, that it's actually this is acceptable, and you actually get considerably decent decent throughput on these type of applications. So this is kind of where this comes into play here. So this, when we talk about massive machine type communications, you're not going to have a sensor that is going to be giving you 10 gigabits per second of data going across millimeter wave. It's going to be longer range. It's going to be much lower data rates and very low power consumption that we're looking over there. So this was kind of a divergence over there. And the first offering that HMS is going to be bringing in the market is going to be in this narrowband IoT space for doing monitoring of sensors. So we've talked a little bit about some of the basics of 5G. Now I want to get into some different applications here. So I want to talk about where some applications where we could see some potential value that 5G can bring. So one of those things I want to kind of bring up is the possibility of, for offshore oil and gas applications is, you're starting to actually see the use of autonomous vehicles in many of these applications there. So, when we think of AGVs, we think of the warehouse videos where we've got AGVs moving throughout warehouses, basically taking, pallets of product and moving it around, between shipping and handling and deployment into inventory, these type of things there. So we see a lot of that, but they're actually starting to develop applications to use them in a broad degree of markets and applications. And for oil and gas, they're actually starting to use autonomous vehicles more oftentimes in offshore applications. So some of them might be using underwater robotics for maintenance in some applications there. But typically for underwater wireless communications, it uses completely different wireless technology than we think for most surface communications. So it uses an acoustic type wireless technology for undersea. But to get access to the broader infrastructure, oftentimes you may have autonomous vehicles that are serving essentially as data gateways. And in this cases, they just can use 5G communications to interact between the autonomous surface vehicle, which oftentimes is used essentially as a wireless gateway to talk to the underwater equipment. And this can be used to talk to vehicles. This can also be used to acquire data from subsea sensors that might be monitoring seismic activity. So a lot of these things can be deployed from an offshore rig with staff on board to basically monitor certain underwater scenarios there. In those cases, typically 5G would be your local network. So this comes back to what I was talking about in terms of CBRS, where a platform like this could have its own 5G network, its own piece of spectrum to talk to deployed autonomous vehicles that are working from the surface and then communicating to sensors. And this creates basically, extremely reliable, high speed, low latency transmission of data. Could be safety for managing multiple AGVs out on the water so that you're not, running extremely expensive assets into each other. It could be used for rapid return of data if, they're basically monitoring subsea sensors for, seismic activity, being able to rapidly alert onboard staff of any kind of impending event so that they can take safety precautions there. So protecting your workers from that standpoint there. So there's significant benefits to this in terms of being able to have these local networks off of these assets there, and then data can be passed typically over satellite, and that would be kind of your central monitoring station there. But in this case, once again, 5G is more than just a broader cellular network. It's actually functioning as a local network in this type of application there. For onshore oil and gas applications, typically if I have remote, several oil well sites that are out in the field somewhere, I could create actually local networks around those multiple sites where I may have multiple wells in place that I can monitor data coming off of there. So I can do things, I can basically have a local 5G network that's monitoring site security. So with a high throughput that I have as part of 5G and the low latency, I can actually legitimately do video back from these sites over a cellular network. I could also do condition monitoring. So coming back to the massive machine type communications, I could have installed temperature and vibration sensors on pumps to do condition monitoring on those. I may be monitoring level at these sites as well for if I have storage tanks to make sure that I don't get into an overflow condition and I get rapid response and those type of things there. So I can monitor those things from basically a local or a sub-regional aspect. And then I can use, either, a private backhaul that could be based off of 5G. Maybe I'm leasing a little bit of AT&T spectrum, or a 4G LTE backhaul, or potentially even something along those 900 megahertz or some other type of lease spectrum. I can use that for my private. But I could also have a local 5G network that would allow connectivity for operators to be able to monitor their equipment there, so that they're making sure that they don't go into EPA violations with a tank overflow. They can, if they have problems with pump motors or anything, they know they can monitor these things and know before they happen, so they can reduce their cost of maintenance. And then additionally, if they have concerns about the security of those sites, they can also do that as well. These things over 5G networks. So in addition to oil and gas, these can have potential applications for water and wastewater applications. So either booster pumps or lift stations, these type of applications. Many of the same principles apply. If you're moving oil on onshore, you've got pumps in there. Water and wastewater, many of the same things. You've got pumps in there as well. So you're worried about the condition of your pumps. You're worried about level in a lift station because you don't want to flood a subdivision and incur EPA fines. So this is critical for water, wastewater districts, these type of things there. Site security, they have valuable equipment in there. They want to keep an eye on that, make sure that somebody isn't tampering with that equipment. So a lot of these things are critical issues for there as well. In those cases, you could have a 5G network that has the core that's connected back to the central plan. Once again, that could be their own network that they have there. So their own spectrum, and then it could be connected up to their sites remotely. using 5G as a technology. And then they're actually getting, you know, higher throughput, higher number of devices they can connect in there. So it's ultimately quite scalable from that standpoint. And then in energy, so there's also some of you may have heard things like demand response type control applications. So what some companies are actually doing is they are providing supplemental energy. So this is actually a way of basically creating, you know, profit out of providing additional energy. So some companies, what they do is they will monitor the market prices for energy, and then they will have assets like generators that they can actually then control and turn on when market prices reach a certain point, and then they can basically they sell that energy back to the energy companies. So that's something they can do there. So they're actually looking to do control over over you know, remote networks. So in this case, 5G becomes a more of a rapid response type network for them with low latency, where they can say they can monitor, you know, market prices, and then when it hits basically a sell point for them, they turn their stuff on and they start selling that to the energy companies, you know, based off of, you know, the demand out there and then the price to the market at that point. So based off of how effectively they can control these assets, this puts a lot more money in their pocket from that standpoint. So one of the things they want to monitor is they want to be able to control those assets, and they also want to make sure that those assets are ready. So if I'm, you know, controlling generators and feeding that back into the grid, I want to make sure hey, I've got fuel in them, that I've got battery so I can start the thing up, you know, and then I can monitor the controls and make sure everything is in good operating order there. So in summary, just to come back to things, so you know, what are some of the benefits of 5G? We see the scalability. So this is something that we're going to be able to handle, potentially a network that will handle, you know, millions and millions of devices connected on there. With the ultra reliable latency protocols on there, you've got the reliability aspects of it as well. So it's for time critical and error sensitive applications. We have, you know, extremely reliable networks with extremely low latency. And then, you know, performance standpoint, you know, they're actually looking at this from the standpoint of, you know, now we can start to do, you know, full infrastructure replacement of, you know, physical networks with wireless networks. There's still more that has to be addressed on this. You know, one of the things that now that they're looking at 5G as kind of an infrastructure, you know, there's going to be questions around security, things that have to be addressed there. You know, what's going to be the intrinsic part of security within the 5G specification itself? Is it going to rely on other, you know, security standards being built around it, you know, for, you know, internet type connectivity applications? So there's a lot happening there, but, you know, long term, this is going to have changes in our industry, and it's going to have significant impact on that. So that closes my part of the presentation. At this point, I think, Wayne, we want to open it up to questions.
Yep. So we got a few minutes left before the top of the hour, so definitely, since we're all online, things are a little different than normal. So you can type in a question to the chat panel or the Q&A panel, or if you raise your hand, I can unmute your line. So we'll give everybody a few moments here to conjure up questions. I'm sure there are some out there. That was a lot of good technical information there, Jason. So I really appreciate that presentation. You can also tell your dog's good boy and give him a treat there for not interrupting you.
Yeah, they're pretty good.
Dean, so we'll allow Dean to speak.
All right, thanks. Yeah, Jason, that was a very good presentation. So the question I had initially asked, which I think you answered, but I just want to verify, is on these key services, the broadband, the massive machine communications, and the low latency, are those, is it you get all three or you get two of the three? I mean, I would think, I think you mentioned that the broadband and the mass communications or machine communications, those probably are mutually exclusive, but latency could ride with either one. Is that correct?
Yeah. Basically massive machine type communications are going to be that is going to be a completely different part of the spectrum. So it's going to be a different size. So you're not going to get the high data rates because it's not going to be at the higher end of the spectrum. These are typically going to be sub 1 gigahertz communications there. So, when they promise, for example, and I just qualify some things here a little bit, when they talk about 10 gigabits per second, it's not that every frequency that you use, you're going to get that 10 gigabits per second. Now, the devices, the phones that function on 5G and so forth, and devices that function on 5G will support things like MIMO. So that's geared around a lot of the reliability there. So that's going to be something that's going to be pretty standard on those devices there that have 5G. Narrowband IoT, maybe not. So that's going to be kind of its own subset of applications there, and it's going to be uniquely different from a lot of the enhanced mobile broadband and the ultra reliable low latency communications, which will typically function at the higher data rates, the higher spectrums, and also within ultra reliable low latency communications really is it's a methodology that's built over it. So it's not necessarily frequency reliant, it's just a methodology that's built on it. But most people who are doing, for example, mass machine type communications won't necessarily, use a URLLC implementation.
Okay, no, that's very helpful. Thank you. I'll give you one more follow-up question. So, kind of where are we in the whole adoption of 5G, or what's your best guess on kind of where we are and where things are going in the timeline?
Yep. So if a lot of us, if we looked at our phones today, oftentimes we see things like, depending on who you're using, you'll see things like 5G Edge on there. So what's out there in terms of 5G is nothing. And what's true in terms of what is true 5G? The things that can be supported today are things like narrowband IoT, a lot of the massive machine type communications types things. Those standards have evolved, and there's actually radios that will handle that. For a lot of the higher speed communications, while the cellular providers are starting to build out some infrastructure, the radios really don't exist for the user end devices yet. So in terms of implementation, it's still a ways off. What we're talking about in terms of radios, we're looking middle of 2020 towards the back end of 2020 is before they start coming out with basically what they call the new radio, basically as a 5G NR. That's going to be able to take advantage of millimeter wave, the higher end parts of the frequency spectrum, and that's also going to be able to do ultra reliable low latency communication implementations. Those are going to need to be in the new radios, and those are not out on the market yet. So we're looking 3 to 6 months before the radios are out on the market. For industrial products, I'm going to guess it's probably another 12 to 18 months after that. So realistically, we probably won't see a lot of devices that can support this, probably till late 2021, 22 would be my best guess scenario there, just based off of, based on when something becomes available and how long it takes a company to bring a product to market.
Thank you.
All right. I don't see any other questions at the moment, so we'll just give one last call there. And in summary, again, want to thank Jason and Howard with HMS Networks for really kind of putting this together and being flexible. I know, like we said, we had every expectation of having those two guys here in New Orleans today, which would have been great to have this presentation live. I thought, again, it was a lot of good information. But we're all flexible right now, right? So we appreciate everybody joining us from online, and hopefully everybody is staying safe and healthy, and we will meet up again in April in hopefully a much different set of circumstances. So all right, we'll wrap it up. Again, thank you, Jason. Appreciate the time.
Thank you, everyone.
All right.
Thanks, Wayne.
Yep. Thanks, guys.